Today we'll be looking at the theory of acid and bases, part 1, acid-base definitions and calculations. The assessment criteria that we'll be looking at will be understanding acidity and alkalinity in aqueous solutions and the approaches of Arrhenius and Bronsted-Lowry. We will also recognize that in aqueous solutions, acids are proton donors and bases are proton acceptors. We'll also look at pH and determine that pH is the negative log 10 of the hydrogen ion concentration and do calculations with pH. We'll also be able to calculate the pH of a strong acid, to know that water is weakly dissociated, to know that the ionic product of water Kw is a product of the hydrogen ion concentration and the hydroxide concentration. We'll be able to calculate the pH of a strong base, and we'll also be able to understand that weak acids and weak bases dissociate slightly in water. Additionally, we'll be able to write and perform calculations with the acid dissociation constant, to know that pKa, pKb, and pKw, and to be able to use the equations. We'll be able to understand how to obtain and work with pH curves to choose an appropriate indicator. We'll understand indicators as having a characteristic pH and be able to choose them correctly. And we'll be able to carry out titrations and the associated calculations. There is an evolution of thinking about acids and bases. Arrhenius was the first to talk about a definition for acids and bases. After Arrhenius, dissociation as an equilibrium process was discussed to come up with a reason for the varying strengths of acids. The introduction of a pH scale was provided to compare acidity to basicity. And the expansion of the idea of a base was provided with the Bronsted-Lowry definitions of acid and bases. And currently, the most recent evolution on acids and bases is to define acids and bases as with the Lewis acid-base definition. Our assessment criteria is to understand acidity and alkalinity and compare that in the aqueous phase to Arrhenius and Bronsted-Lowry. Arrhenius said an acid was a substance that had hydrogen in its formula and dissociates in water to yield H+. Arrhenius says that a base is a substance that has a hydroxide or an OH in its formula and dissociates in water to yield OH. Bronsted-Lowry defines acids and bases as proton donors and proton acceptors. As long as the solution is water, the Arrhenius definition and the Bronsted-Lowry definition are the same. They're equivalent. Arrhenius, not long after his statement of what an acid was and what a base was, thought that he might have to expand his definition. He looked at ammonia. Ammonia is a substance that has H in it. Therefore, according to his definition, it should be an acid. However, NH3 had basic properties. So an expansion of an acid-base definition was required. Now, in aqueous solutions, acids are proton donors and bases are proton acceptors. Really, an acid-base solution or reaction is a transfer of protons, one donating, one accepting. If you define an acid-base reaction by the Bronsted-Lowry definition, then you can talk about two gases being acids and bases in non-aqueous solutions. You can talk about heterogeneous mixtures. And of course, you can talk about aqueous solutions. Understand pH as negative log 10 of the hydrogen ion concentration and be able to convert pH to concentration and the reverse. In aqueous solutions, hydrogen ion concentrations can vary from 15 molar to 10 to the minus 15 molar. That's a very wide range. To handle numbers with negative exponents, we decided, or it was decided, to use the pH system. The pH system is using logarithms. For example, what is the pH of 10 to the minus 12 molar hydrogen ion solution? It is the negative log of 10 to the minus 12, or a pH of 12. A pH of 1 means that the hydrogen ion concentration is minus log 10 to the minus 1. Now, the next assessment criteria is calculating the pH of a strong acid. By its definition, strong acids are acids that dissociate completely. That is, the hydrogen plus ion dissociates completely in solution. Therefore, the hydrogen ion concentration and the concentration of the strong acid are the same. For an example, in an art restoration process, a museum worker prepares copper etching solutions by diluting concentrated nitric acid to 2 molar. Calculate the pH of the solution at 25 C. The hydrogen ion concentration is the same as the concentration of the acid that was diluted. So therefore, the pH is a negative log to the base 10 of 2, or a negative 0.3. Now, even water is weakly dissociated into hydrogen ions and hydroxide ions. Even water that has been distilled and deionized repeatedly exhibits a tiny conductance. That means it carries an electrical charge. The reason is that water slightly dissociates in an equilibrium process known as autoionization or self-ionization. Because of this autoionization of water, the equilibrium constant is, as we've done before, Kc equals hydrogen ion concentration times hydroxide concentration divided by the water concentration to the second power, and Kw is equal to the H plus concentration times OH minus concentration. That means that one hydrogen ion and one hydroxide ion appear for each water molecule. So in pure water, the concentration of hydrogen ions equals the concentration of hydroxide ions equals the square root of 1 times 10 to the minus 14, or 1 times 10 to the minus 7 which is a pH of 7, which is neutral. Pure water has a concentration of 55 molar. So these equilibrium concentrations are reached when only 1 in 555 million water molecules dissociates reversibly into ions. Let's see how we can use our understanding of the pH of a strong acid in finding out the concentration of the pH of a strong base. Let's use the same art restoration process. In this case, we have the nitric acid being diluted to 0.3 molar. What is the pH of the base? In a strong base, just as the hydrogen ion concentration is dissociated like the strong acid is dissociated, we'll use a hydrogen concentration of 0.3. We'll use the formula Kw equals hydrogen ion concentration times hydroxide concentration. We know that at 25 C, Kw is equal to 1 times 10 to the minus 14. We solve for the hydroxide concentration, which is 3.3 times 10 to the minus 14. And if we want to make a POH, we can use the negative log, and we find it to be 13.48. Now, weak acids and weak bases do not dissociate completely. They dissociate slightly in water. So, we cannot assume that the molarity of the solution is also the molarity of the hydrogen ion concentration. We have to take into account the acid dissociation constant. Let's look at a weak acid, HA. We add water to it, it dissociates some into hydrogen ions and A- ions. The Ka, just like we did with equilibrium, is the hydrogen ion concentration times the A- concentration divided by the HA concentration. Let's look at a short video that talks more about this dissociation in more detail.
The strength of an acid refers to the extent that it dissociates into ions when dissolved in water. Strong acids dissociate nearly completely. Weak acids dissociate very slightly. Dissociation into ions means that when an acid, HA, dissolves in water, it transfers a proton to one of the water's lone electron pairs, and the acid anion, A-, and a hydronium ion, H3O+, form. The color change of the water oxygen will make it easier to follow in solution later. The key difference between strong and weak acid dissociation is the final concentration of hydronium ion in solution. Since proton transfer from a strong acid to water is nearly complete, the hydronium ion concentration is essentially the same as the original acid concentration. In contrast, proton transfer from a weak acid to water becomes balanced by proton transfer from hydronium ion to A-. So the final hydronium ion concentration is much less than the original acid concentration. Let's view acid dissociation at the molecular level and focus first on strong acids. The concentrated acid in the beaker consists primarily of acid molecules. As soon as they make contact with the water in the flask, proton transfer from HA to H2O occurs for virtually every acid molecule. Note the change from blue to red. Therefore, a strong acid solution consists of hydronium and A- ions in water and virtually no HA. It follows that the acid dissociation constant Ka for a strong acid is very large. Now the beaker contains a weak acid. As before, the moment the acid molecules make contact with the water, proton transfer from Ha to H2O occurs. But in a very short time, proton transfer from hydronium ion to A- balances it, and equilibrium is reached. Thus, a weak acid solution has a relatively high concentration of Ha and very low concentrations of H3O+ and A-. Therefore, the acid dissociation constant is very small.
So to continue, in looking at weak acids and weak bases, after we write the balanced equation, we define X as the unknown concentration that changes during the reaction. Frequently, X equals the dissociation of HA, the concentration of HA that dissociates, which through certain assumptions also equals H plus and A minus at equilibrium. We then construct a reaction table that incorporates the unknown, assuming that X is very small relative to the initial concentration. It's a weak acid, right? Then we substitute the values in the Ka expression and solve for X. Looks a lot like the equilibrium concentration problems we did at greater than a power of 2. Know pKa, pKb, and pKw, and be able to use the equation pKw equals pKa plus pKb. Well, for a strong acid, the pH plus the pOH equals pKw, or the hydrogen ion concentration times the hydroxide concentration is equal to Kw. For weak acids, pKa plus pKb equals pK, and Ka times Kb equals Kw. Now, to solve a problem for a strong acid, if the acid's pH is 3, then the base's pH, or the pOH, is 11, because 3 plus 11 equals 14. However, if we have a weak acid, we must be provided with the pKa to determine the pH. For example, if acetic acid, a weak acid, has a pKa of 3.38, then 3.38 plus pKb equals 14. And you can do the math. We are going to talk about indicators a good many times during the 12th grade year. We will, though, also talk about indicators and how we choose indicators. One of the ways we choose indicators is with pH curves. The examples below look at a strong acid versus a strong base and a strong acid versus a weak base. The indicators discussed are phenolphthalein and methyl orange. Phenolphthalein goes from clear to a purple color. Methyl orange goes from yellow to orange. Now, if you remember in titrations, we want to end up with a pH of 7. So, if we have a strong acid versus a strong base, we can look at the pH curve. Notice how steep the pH curve is for a strong acid versus a strong base. There is virtually no difference in the volume of acid added, whichever indicator you choose. The line is almost straight up and down. So you could use methyl orange or phenolphthalein as an indicator. Let's look at a strong acid versus a weak base. Again, phenolphthalein turns from clear to 7, a little bit above 7, and methyl orange turns from yellow to orange, a little bit below 7. But here, the straight line up and down goes through methyl orange, and a much less steep slope goes through phenolphthalein. So it would be much more appropriate to use methyl orange for a strong acid versus a weak base. We'll look at other examples of choosing acid-base indicators with pH curves in class. Another assessment criteria is to carry out titrations and the associated calculations. We've done this on more than one occasion in Chemistry 11. In Chemistry 12, you'll be required to do it at the end of the year in the practical examination of the Cambridge certification. As a class this year, you investigated different indicators. We won't discuss titrations at this point because you will get much practice during this school year. I'll provide these questions for you to think about. Remember, with questions to think about, I would ask that you provide a detailed answer on why your choice is correct and provide them to me when asked during the revision process during the 12th grade school year.